We're going to look at spring and mass for simple harmonic motion. And it is simple harmonic motion, meaning it moves symmetrically around an equilibrium point, equilibrium point. And that equilibrium point is if this is on a frictionless surface, this mass would just rest there. Okay, that's its comfortable place. And it's also characterized by a restoring force that's proportional to the distance delta x, or the displacement from that equilibrium point. So the farther I pull this thing back, the more force there's going to be towards the center. And the same here, if I push it in, the more force there's going to be towards the center. What's really important in these and all spring problems is that the force is not constant. Okay, right there the restoring force would be zero. The spring force is zero. It's only as it moves away from the equilibrium point that that force increases. Pardon me. So since that force is not constant, you can't use it to do things like work. A lot of students make mistakes by they know this lovely equation, which is a great equation, Fs equals k delta x. And I'm not going to worry about the directions right now. The force is opposite, so we generally put it this way if we're talking about vectors. But the students will use this and then plug that in to find work, and they do all sorts of weird things that I don't love. So if we're talking about one location, fantastic. If you're talking about one specific location, then yes. If you know the spring constant and you know the displacement, then you know the force there. And you could use that to find the acceleration of the object. That's a really nice thing. But if we're talking about a lot of the problems that have to do with velocity and displacement and all that, you really have to solve with energy, conservation of energy. Okay, so it's going to go back and forth between these points. And if you remember with a pendulum, we did a lot of problems that involved the period, the equation that we had for the period. Period is equal to 2 pi square root of L over G. And this has a similar equation. The period for a spring and mass is going to be 2 pi, looks the same. Square root, that looks the same. Well, think of what's going to happen. Mass, a big mass is going to be harder to move back and forth, right? So that would be a bigger period. So the mass is on top, and if you're interested, I derived this in another video. And the spring constant, if the spring constant is big, it's going to push back towards the center more strongly with a greater acceleration. So that would make it a smaller period. So that's your equation there. 2 pi square root of m over k gives you the period of the spring. Frequency is just 1 over the period. So it's 1 over 2 pi square root of k over m. And those are really nice, useful relationships. And then for AP Physics 1, we also have an equation for x as a function of t. The general equation we're going to use is A, amplitude. And amplitude, we've got a positive and negative amplitude, depending on what you call positive. Amplitude times the cosine of 2 pi ft. What's different in other physics? In other physics, this could be sine, and you could have a phase shift plus phi. That allows you to take a generic sinusoid and shift it to the right or the left. And that would allow you to get anything, any kind of description. This description, when we talk about time being zero, cosine of zero is 1. So it's at the amplitude at the beginning for this description. Again, that's okay for AP Physics 1. That's like pulling this out and saying when time starts, we let it go. okay? So it will go back here, it will go back here in half a period, and then it'll come back here in, that would be one entire period. Another thing you see sometimes is this 2 pi f is sometimes written as omega. Okay, so with these tools, we can solve many problems involving spring and mass. And so, as an example, if I have a, let's say I have a 1 kilogram mass and spring constant K of, I'm going to make it 100 newtons per meter. Well, right away, I can get the period is going to be 2 pi times square root of 1 over 100, 0.01. That just ends up being 0.1. 0.1 times 2 pi is about 0.628 seconds. Frequency would be 1 over 0.628. We measure it in hertz. I would normally calculate that out, but I don't want to take the time on this. So once we've got that frequency, we can put it in here. And if I said, where is it? Oh, I've got to have an amplitude. If I had an amplitude of, let's say 0.2 meters, so I pull it back 20 centimeters, I could calculate where it is at any given time, because it's going to be 0.2 times the cosine of 2 pi times 1 over 0.628. Again, I would normally calculate that out, times t. Okay, so if I gave you a time, you could figure out where it is. So that's one nice thing about springs and masses, is it's very similar to pendulum with a different expression for period. Last thing I'm going to do is I'm going to talk about vertical springs and masses. Well, when you hang, let's say we've got a spring here, okay? When I hang a mass on it, it's going to come to a new equilibrium position. And that new equilibrium position, if this is my delta x, I know the free body diagram says mg has to be equal to k times delta x. That's the spring force. So I can find out for a spring constant and mg, I can find out where that new location is, how far it will fall. If I had mg and the displacement, I could find what k is. So this is at rest. A nice thing about springs and masses vertically is you'd think, oh my gosh, now I've got a different deal that I've got to work with. I'm not going to derive it for you. But the bottom line is now it will go in simple, if I give it a displacement, it will go in simple harmonic motion about that new equilibrium. And it'll have the exact same behavior as before. The period is still going to be 2 pi square root of m over k, just like before. And x of t is still going to be, if that's my a and that's my negative a cosine of 2 pi f times t. So it's no different. In these situations, for vertical problems, all you have to do is figure out how far did it go down? And that's doable with a very easy free body diagram. And again, this is the spring force here, only when it's at rest. Okay? And then it will oscillate around that new equilibrium point. So it's exactly the way you did the horizontal one, but it's a little lower than it would have been. So it's just shifted down. Okay? That's all I'm going to talk about right now for spring and mass. In the next video, I'll talk about energy, conservation of energy, particularly for springs and masses.